And then I assume everybody can see the whiteboard, right? Yep. Okay, awesome. Okay, so let's at least just start with a basic rundown of what a cache is and what it does. Oh, I need to move my pen as well. Play to play. Okay. Got a lot of yeses. Okay. So a cache, I mean, like the name kind of implies, it keeps a cache of variables and instructions that that you might be using in memory. So we have the CPU. I guess that's probably not a good thing. Yeah, let's just do it that way. So we got the CPU, and then we've got main memory, so like RAM. And so when we have to get variables from main memory and move them into the CPU so that we can actually do process on it, then it takes a long time, at least comparative to just transferring things between registers. And that just boils down to a couple of things. One, it has to access the bus in order to actually get the main memory, or the memory from main memory into the CPU to use. And then on top of that, God, I totally lost my train of thought. So it has to access the bus, and then sorry, yeah, I remember what I was going to say. And then the actual hardware itself is kind of slow, at least compared to the CPU memory. So let's take a closer look at what's actually in the CPU. So we have, that doesn't look like a CPU. So in the CPU itself, we have cores. So we could have like core 0, core 1, ... core n. So the solution to that, to try to get some speed up, is to throw a cache. And you'll usually see that there are several levels of cache, and each one gets bigger over time. So what we typically have is an L1 cache for every single core. So from core 0 to core n, I guess you could consider that core n minus 1 if you really wanted to. We have an L1 cache, and really that's just a memory bank that holds variables or instructions similar to RAM does, or the way RAM does. So the only real difference between these is that this is much smaller. So main memory, if you have RAM in a computer, it's probably, somewhere between 4 gigabytes, 16 gigabytes, something like that on a modern computer. These are closer to maybe just a few kilobytes, at least in the L1 cache, and it depends on the actual processor that you're buying. But each one of these essentially has its own cache. And so this addresses both of those issues that we had earlier. So it doesn't have to access the actual computer bus, it just has to access this little bus right here that's going to transfer it directly from the cache to the core. And so that's good because it's a shorter distance. It doesn't have to compete with a bunch of other things trying to access the bus. And then on top of that, these are actually made out of different materials. So in general, RAM is... So like the sticks of RAM that you buy are DRAM, which is just dynamic RAM. And that's pretty good because it's relatively cheap to get a couple gigabytes of that. And then the cache, or the caches, use SRAM, which is static RAM. And that's more expensive in terms of like actual money, not time, compared to DRAM. So that's why we don't use a whole lot of it. You could, in theory, use it for your main memory for your computer, but it would inflate the cost a lot, and that's not very realistic for most people. So we typically use this better, faster RAM, but it costs more money. And so we only use a little bit of it in comparison. So just to continue with that, we typically have, on most computers, an L2 cache and an L3 cache as well. So actually, I believe the way that Intel does their architecture, we have an L2 cache. I guess I should draw that a little bit differently. It's a little bit bigger. Than the L1 cache. So as we go out and get further and further away from the CPU, generally these memory spaces become bigger. So this might be a few kilobytes, this might be double the size, and then the final one I'm going to do here might be like a megabyte or a couple megabytes. And then obviously your main memory is probably a few gigabytes. So generally, at least this is the x86 architecture that I saw, but it might be different on other processors. Each core gets an L1 cache, a slightly bigger L2 cache, and then all of these share one big L3 cache. So what this does, I guess just to go back to it, is it stores variables from main memory. So we might have like int x somewhere in here. What it does is, rather than have to go out there constantly, it will store a copy of it in the cache. And there might be actually several copies of these in all three caches at the same time. So let's just say integer x, somewhere in our code we end up using it so that it needs to be added to something. So core 0, let's just say, handles that instruction. So what it'll do is it will throw that in the L1 cache, the L2 cache, and the L3 cache, and core 0 now can just, whenever it needs the integer x, just go straight to L1 cache. Now, I believe you guys talked about cache hits and cache misses, right? Yes? Okay, awesome. So if it finds it in that cache, it'll get a cache hit. And if it misses, it'll get a cache miss. And if you remember, I'm sure Dr. Fonseca talked about it, a cache miss is way, way, way more expensive than a cache hit. At least when we get a cache miss across all three. So what it does, let's just say I use integer x in some addition. So let's just say I have some C++ code up here that's like x equals 3 plus 5 or something like that. And then I go down here and I say, well, x equals x plus 7. So I use it twice in a row. So what the CPU does, the first time, so let's just say this is the first line in your code where x is used. Obviously, x can't be in the cache at that point because it was never initialized. It wasn't, not initialized. It might have been declared, at which point, it has some memory allocated, but it hasn't been used for any computation yet. Actually, this is probably better if I just... This is fine. Let me do this a little differently. Let's just initialize it up here, and then let me use it twice on the right-hand side, because I think that's more realistic. Sorry if that's a bit small up at the top. So let's just say x equals 5 was what we started with. We did some sort of initialization of it, just so it got allocated into memory and used. So we use it twice here. So the first time we use it, oh yeah, sorry. What were you gonna say?
No, sorry.
Oh, okay, that's all right. Right, so this is like the first time we use it in any computation. So the first one was just an initialization. This is the first computation. What's going to happen is x hasn't been used at any point before. So we need to take x and load it into the cache. So what should happen is it'll get loaded into the L3 cache, the L2 cache, and the L1 cache, assuming that the computation is going to be done by core 0. if it was done on a different core, it would also fill the caches associated with that core. So what happens here on the next step, so we use X immediately afterwards in this C program that I wrote. So what's likely to happen is that X is still in the cache because it was used really recently. You'll find later, Dr. Fonseca should talk about it, that the least frequent, or if you don't use it very frequently, it will get overwritten in the cache because the cache is kind of small, at least in comparison to main memory. So what it does on the second computation is it looks for X, and since it was used recently, it's probably going to be an L1 cache, which would be a cache hit. But if it misses, if it didn't find X in there for some reason, it would have to check L2 cache next, and then the L3 cache, and then if it misses on all three of those, it will then go to main memory. And the nice thing about missing on L1 and L2 caches is the fact that you're only searching a cache after that, which, if a cache hit is when you find it, right? A cache miss is when you have to go search somewhere else for it. If you miss on these ones, you're searching something that's also very fast and also very close to the CPU, so it doesn't take a whole lot of time. Once you get this miss on the L3 cache, then that's when we start to have a lot of overhead. We have to go all the way to main memory, retrieve the variable, and then store it in the cache. Any questions on that basic setup so far?
So when you retrieve something from main memory, does it get copied into all three caches?
Yes, so it should, I believe the way it goes, is if it's in any cache here, it's also got to be in any memory space to the right of it. So it might actually get overwritten in L1 cache, but still exist in L2 cache. And that kind of works with the way we do the hits and the miss, right? If we miss on the first cache, then there has to be a chance that we can hit it on the L2 cache or the L3 cache. So it has to exist. If it exists in one, it has to exist in all the ones to a higher level, I guess, or to the right of it in the diagram I drew. Does that answer your question?
Yes, thank you.
Sweet. Any other questions on that?
I think I have a question. So, if the value of X is modified in the L1 cache, then X would be a different value than in main memory. Is that correct?
Good. Yeah. Thank you for catching on to that too. I'll actually address that in a little bit, but good question. Yeah, that is a consideration we do have to take. Okay, so I think we'll move on, and actually, I'll probably address that question if anything. Structure. Yeah, because everything else I think I have written down here I want to talk about is programming related. So yeah, to answer your question, that's a good point. So let's say we have main memory over here. And I'm going to do just a very brief version of this. But realistically, that's a little big. Oh well, it's fine. Realistically, there's more to it. I didn't see it anywhere in the textbook. It seems like they removed it for the 11th edition about like the actual like technical details about this. But if you're interested later, I would say look up set associative mapping and direct mapping of cache. And maybe Dr. Fonseca will cover it. I just didn't see it anywhere in the book. But anyways, let's just say we have main memory. And we have values in here, ... And this is address 0. This is address 1. Address 2. Address 3. And then we have the cache over here. So what you'll see in the cache is that it's a series of lines. And so what happens is each line is usually larger than each actual addressable word in main memory. So this might be, let's just say, for example, this might be 32 bits, and then this one over here might be 16-bit per line. And the reason we have more space per line on cache than in main memory is for two reasons. Actually, I guess, let me make this 64. I guess it should be quite a bit bigger. And again, just consider this is just a random example. It could be totally different on some machine. There's some stuff on direct versus associative in Section 5.2. Oh, okay. Then I guess Dr. Fonseca will cover it, because he told me just to do 5.1. Although I would definitely look into that between now and Monday, because I think that stuff can be a little hard to wrap your head around. But anyways, yeah, so in the cache we have these long lines, and then we have main memory. And so again, we want to make copies of this that we'll keep. So one thing we'll just throw here that somebody just mentioned was we want to keep track of whether the actual data has been modified in main memory. Because if that's the case, then we shouldn't be using it, right? Because then it's not updated. And an example of that might be, this is the cache for core 0, and core 1 was also doing something in parallel where it modified the same variable. So maybe core 0 is doing addition on X, and then core 1 does some sort of write to X. Maybe there's some sort of storage in the variable X. So then it's going to get updated in main memory. So what it does to keep track of that is it keeps just one bit in the data that's a validity bit that just keeps track of 0 or 1. Is this data actually valid? Has it been updated from main memory? And so what I believe happens is it just checks every once in a while and updates this, but the CPU doesn't actually have to spend computation time doing that. That's probably something that the memory management unit does, if anything. Yeah, so that was a good question earlier. They do keep track of that. There's a validity bet, and then we have basically a tag and a block. And the tag will be a few bits, and it depends on the size of your memory space. But what we do here is we obviously don't want to spend a whole lot keeping track of like the actual full address of this. So, for the sake of this, maybe I should make this a little bit longer on the addresses. So let's just make it 2 bytes instead. 00 hex 00 hex 00 02 01 hex 00 03, and then we'll say ... and then maybe hex 0100 hex 0101 hex 1 2, something like that. So it would be kind of inefficient to store all of this memory here, like the entire address along with everything. So what we usually do is we split this up into blocks. So this here might be a block, so this might be block 0. And then this might be block 1, and then we would keep going until we're entirely out of memory. And the way we end up divvying this up, and you might notice the pattern from what I have, is we pick some amount of bits in the beginning, and we might actually end up calculating how we would do this with a memory space, and let those be the tag that determines the block. So everything with the first 2 bits, first 2 nibbles, like 1 byte 0, is going to be in block 0. Everything with the first byte 1 will be in block 1, and then after that we just have the index, essentially. And you'll notice it repeats across both of these. Oops, I didn't mean to put block there. I should probably make this a little bit longer. So let's just say I have more down here, and it's hex, 4, and then the same pattern. So 0001 up until FF. ... Put that down there. Okay. So what we'll do is we'll just look at the block itself. So what this will do is we'll copy actually an entire block, and these are relatively small, maybe a few kilobytes, and put it into the cache. So what it might do is first take block 0, put it in the cache, and then copy over all of the data from block 0, so all of the variables in there. And then it might copy over tag 1, which again is just this these first 2 bits, and then put it in the cache. So what we usually do to save space, just because we're going to have way more memory and more addresses here than we could possibly fit in cache, right? Otherwise, we kind of defeat the purpose of using main memory versus this, because we could just replace all the main memory with cache. What we usually end up doing is take that first tag bit. I don't know if I want to call it that. I don't know if there's a technical term, but let's just call this like a header. Okay, maybe most significant bits. That's probably more descriptive. We take that and we modulus it by how many lines we have in the cache. And the reason being, if we modulus it by that, then we know that the amount is limited to a value between that, right? 0 and lines minus 1. So we'll have exactly the amount of lines. We know we'll always be able to fit it in the cache. And then that equals the tag. So that's the general strategy. So if I was to take something from block 0, it's going to end up with tag 0 because, oh, whoops. Again, probably should draw this a little bit more accurately. Let's just say there's only 4 lines in the cache. You hash the cache. Yeah, good pun. Solid. But yeah, we are kind of hashing it, right? So let's say we have 4 lines here, and then we have this memory space where we have block 0, block 1, block 4. Now in this specific example, because of the size of the cache, we are... Yeah, this is fine. If I was to put in block 0, its tag is going to be 0 because 0 mod 4 equals 0. So that's its tag. If I was to do it with block 1, it would equal to, oh, I'm sorry, wrote that wrong. 1 modulus 4. So if I take the block number and modulus by the lines that I have, I get 1 for that one. And so if I continued on, block 2 would obviously be 2, block 3 would be 3. We get to block 4, and then 4 modulus 4 is equal to 0. So if I was to try to load variables from block 0 or load variables from block 4, they're both going to take the same space because they have the same tag. So what happens is, let's just say I use, and there's a variable x that's in block 0 and a variable y that's in block 4. So in my code, maybe I do, something where it's like sum equals sum plus x. And then I do like 100 lines of code, and then I modify it again where I throw y into there. So the cache is going to first load in variable x, execute all of the code that it needs to, accessing variables as it finds them in the cache. And when it gets down to block 4, it goes in here and it says, well, I don't see block 4. But if I check the tag for it, the tag is 0. So what it will do is it will go in and just overwrite the previous block with that tag. So block 0 will get overwritten, and block 4 will get put in there. And I guess one other thing to note, whenever we refresh the cache or add something into it, the validity bet is always set to 1, and it's only set to 0 if we find out that there is a modification to the memory. So actually, that's a good point. We don't actually necessarily need to refresh on memory. As long as we know that we're writing to that block, we can update the validity bit in another cache. So if core 2 was to modify variable x or block 1 or whatever, it would, block 0, it would change the validity bit to 0 in all the other cores. That way we don't actually have to go to memory and check, well, does it match? But did that make sense, like taking these blocks and putting them, hashing them into the cache, and then we only refresh if we don't find that block in there, we get a cache miss. Ask another calc question. I wish. I mean, I'll talk about some math later, I guess, but it'll be a program. And I'm sorry if I am being a little vague or abstract. I don't want to go into the super detailed stuff on the cache, because I think Dr. Fonseca is going to talk about that. But just it's important to understand the general idea that we store copies of variables in the cache. That way we don't have to go out and get them later. And there's only a little bit of space to store those variables. How does this work with the other levels of the cache? Will they all get updated at the same time every time? So I guess similar to what I was saying earlier, what should happen is whenever you update a variable or fetch a variable from main memory, it will update all the levels of cache on the way to the actual place that it's trying to get. So you mod the blocks before the program executes. No, this is actually all done while programs are executing, and this is all done by hardware. So you have no control over this, actually. And that's something I meant to mention. So you can't, as a programmer, actually physically modify any of this willingly. You can structure your program around it, and I'm going to get to that in a little bit. But it has to modulus it as it gets cache misses. So it's when it does the modulus, it's when it's populating the table. I can't save a var. No, you can't access any CPU space. And neither can the operating system. It can't do it either. The CPU, the actual hardware, is in charge of that. But yeah, I guess to answer that one original question a little more detailed, with the other levels of the cache, anything higher up will always contain either not contain it, in which case it's a miss, or will contain the actual correct version of it. So again, memory is technically, like main memory is higher than all of these on that. So main memory is always going to contain the correct variable state, right? So anything to the left of it might contain the correct updated variable, but it might also not. In which case it's a miss. Any other questions on that? Again, I know I'm keeping it a little vague. Does that make sense? Okay. I guess if anybody has any other questions, just stop me. Okay, so let's see what else I got written in. Yeah, I think the rest of it's just examples. Oh, actually, one other thing I wanted to note, because I saw it in the book and some other references. Oh man, I've just written so much on these things, it's kind of disorderly. Core 0. This is just the processor. The L1 cache will contain both data and instructions. So it might not just actually contain variable data, it might also include physical opcode with an operand that it needs to fetch and then decode and execute. But the L2 and L3 cache, generally, again, this is what I was looking up was x86, so Intel's architecture. They only store data in the L2 and L3 cache. So it's just something to note, not super major. Okay, so let's do a couple examples of programming when you might need to consider the cache. So I'm going to write two programs here, and then somebody just tell me which one you think is better. So let's just say I have an array of doubles, double x, and let's just say we have some constant size here. Maybe I should put a constant at the top. In fact, I should probably put this in the middle. Constant size equals 100. Constant, no, not constant. Int x size. No. Let's make this like a float or a double. Float. So we basically just have some collection of variables, just numbers, in this x array. And then we'll just say int count equals 0. And then that's good enough. So let's just say this is the program, and then I have two variations of this. So let's just say for some reason, pertaining to the class, you have to take the arithmetic mean, the geometric mean, and the harmonic mean. So obviously, in order to take the arithmetic mean, we add everything, divide. To take the geometric mean, we multiply by everything, and then divide. And then for the harmonic mean, we take all the reciprocals, add them together, and then divide. So yeah. So let's just say for int I equals 0, I less than size, I plus plus, and then I probably should have declared 3 more variables. So let's say, again, should probably keep it as a float. Float sum equals 0, float product equals 0, and then float, say HAR for harmonic is 0. So let's keep track of all of those. And actually I should probably, just to remind everybody, throw this somewhere. So just as a reminder, I'm sure everybody remembers arithmetic means, so I'm just going to throw that up there. But for geometric, right, we multiply everything. God, that's really small. We multiply everything and then take the root, right? And then harmonic mean, we add all the reciprocals together. And then we basically do the inverse, or like the opposite, and then divide by n, but it's on the top because we're taking reciprocals. There we go. So obviously for arithmetic mean, I just need to add everything up, right? And then I'll divide at the end. So I say sum plus equals, and then again, I'm just using this variable array x sub I, and then product. Oh, I probably want to make that 1, huh? Okay, times equals x sub I, so we're going to just multiply everything together for that one there, and then the harmonic, right, we take 1 over x, and then we're going to multiply by n at the end. So we get harmonic plus equals 1.0 divided by x sub I. So we go through all the array and we do all this. And then right at the end we'll just say some divide equals size. We'll just pretend there's some function that takes the root for us. So let's say product equals the root n product, so it just takes the nth root of it. And then for harmonic, we'll say that equals n times, or rather, n divided by the previous one. So far, is that clear what that program does? I'm just going to write it again and basically over on the side. And I probably won't write all of this. Let's just do at least one really quick. And there's two things we're going to consider with this program. So let's say first, I take the arithmetic, so I do one loop where I calculate it, and then I take sum divide equals size, and then I do the geometric mean next. So I again go from I equals 0, I less than size, I plus plus, and then I again times equals by x sub I. And then I do the same thing where I say product is equal to the nth root of the product. Ignoring the fact that I allocated I twice, which you might notice. And let's just say, I'm not going to write it out, but let's just say we do the the harmonic mean down here as well. Just so that it does all the same code as that one. So there's going to be a performance difference in these two things. And one thing to consider is they're really just going to do the same steps, right? Even though I have 3 different for loops, again, ignoring the fact that I declared I 3 times, really they're just going to do the same computational steps, right? This is just going to add all the numbers, it's just going to multiply it, and then this one's going to add as well, and then they're just going to divide or do whatever they need to. So they're doing the same computational steps, but which one of these is going to be faster and why? One. Yes, you're right. X of I is stored in the cache. Awesome. Thank you. Yeah. Okay, so I think that's good enough. Thank you. Yeah, you guys are right. So the first one, or the left one, is going to be faster. And the reason, like somebody said here, is that x sub I is going to be stored in the cache. So you'll notice here, when I use x sub I, that, and actually there's another reason too, if you notice it doesn't have to do with the cache, and if anybody points it out, that'll be good. But yeah, I use x of I 3 times in a row here, which means it's more likely to be in the cache when I use it versus this one. Because here I'm going to go through all of the variables from x sub 0 to x sub n, or x sub size, whatever, and they're each going to get written to the cache. Whereas this one, I'm reusing the same variable 3 times in a row, I'm more likely to get a cache hit. It doesn't have to load for a new loop. Yeah, or it doesn't have to load the same variables again. Whoa. I don't know how to do that. Yeah, 3 for loops. I mean, obviously, just looking at it, this kind of looks disgusting compared to this one, but just for the sake of the example, why it would have a performance hit versus this one. Does that make sense, though, why this one is going to have cache hits more frequently than this one? And so you should program like this. You should try to put as many things in the same location as possible. Makes sense? Cool. Does anybody else see any performance reasons to use the one on the left that's similar? O of n versus O of 3n. Actually, no, they're both the same time complexity. If you're familiar with time complexity. They are still doing the same computational steps because this one is n this one is n, and this one is n, so this one is still 3n computational steps, and then, plus 3, and then this one's still actually 3n as well. At what point will the cache update? The cache will update if it gets a cache miss. So if it tries to, let's just say, find x sub I, which is more realistic for this one, it's going to get a miss. If it tries to find x sub I, and it's not there, it will get a cache miss, it will go to memory, and then the cache will update. So the only time, just to reiterate, the only time the cache will update is when you get that cache miss. And so if L1 misses and it finds an L2, it will still update the L1 cache. So any cache that it finds a hit in, it will update everything to the left of it. So if I got a hit in L2 but a miss in L1, it will drag everything, it'll copy everything to L1. But if I got a hit in like L3 but I got a miss in L1 and L2, then it will copy the variable to both L2 and L1. Could you run the code on the right in parallel? Yes, you could. Although, if you're running it on the same system, you are still going to get caching issues, probably, because they do still share that L3 core, right? Even if these are running in parallel. So they're still more likely, if they need to use the same variable, that because another core is used x sub I, actually, no, I'm sorry, that wouldn't affect this, right? Because they're all using x sub I. Yeah, one core per loop. Yeah, and they actually are more likely to get cache hits if that's the case. Cat will contain it will contain the variables that you've recently used. So like here, when I do this, let's just say for I equals like 10, this is going to access x sub 10, and then this one will access x sub 10, and then this one will access x sub 10, and then on the next iteration they all access x sub 11. But on this one, it's going to access 0, 1, 2, 3, 4, 5, 6, 7, 8. So the order of execution for these two in terms of i's, this one would be, it accesses I0, 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 I1, 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 and then 2, and then dot 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 in pairs until we get to size minus 1, size minus 1, size minus 1. Whereas this one, we do 0, 1, 2, dot dot dot, size minus 1, 0, 1, 2, dot dot dot, size minus 1. So you'll notice that the same indices, which correspond to a memory address because it's an array, are going to be used the same or closer together than here. So we're more likely to get cache hits because they've been used recently in the cache versus here where the last time I used it was size many steps ago. Does that all make sense? So actually, yeah, one last question I had was, and it's related. What other issues does the one on the right have versus the one on the left that's related to this whole deal with the indices that doesn't have to do with cache that you guys should have learned in the last chapter, I think? What advantage does the one on the left have? I'll give you a hint. It has to do with locality, which applies to the cache. Would the one on the left have temporal or spatial locality over the one on the right? Right. Yeah, everybody's right in the chat. So temporal, right? Because I'm accessing it within the same close time frame. Yeah, awesome. Cool. Does that make sense to everybody? Yeah. Okay, fair enough. All right, so let's just move on to one more example that I had. Unless anybody had any specific questions. I think I only had one more thing written down that I wanted to cover. So, I don't know, maybe we'll go back to that last one. Yeah, let's go back to the last one really quick. Let's do an easier example before we do that. So there's one other thing that might actually totally make this blow up really badly. So we might not even actually have many performance issues if I was to run this program, then run this program with the example I gave. And there's a reason why. So if we look at the size that I gave, and this is why I declared it as a separate variable, why do you think we wouldn't really see a performance issue with this example, and what would change that? Size is small, right? How would that affect it? Or why would size being small affect our cache hit rate? It can all fit in the same cache. Yeah, exactly. So if I have something that's relatively small, like 100, that's not that many floats, right? That'd be 100 times float is 32 bits usually. So that'd be like less than a kilobyte, right? Or no, 3200, about 3 kilobytes. So you can take advantage of temporal locality still. Yeah, right? Yeah, at least on these ones we can take care of the temporal locality. But if I was to increase this to, 10,000, just throw a bunch of zeros there, then this one is still going to have the temporal locality. And then this one is going to be more affected by it because it's more likely that when I get to this iteration here on the geometric part, that I'm more likely to have a cache miss because I used more things. They're more likely to have overwritten stuff in the cache that was already there, and then I get cache misses, and I have to miss on each of these. And if we're using, which Dr. Fonseca will talk about, the least recently used one where you just throw out the last variable, like the one that wasn't used recently, then this one's going to get a lot of hits. And so you notice if you actually executed the times on these, you would probably get a really big time hit on the right program once we actually hit a size for the array that really affects the cache. We want something larger than a block. Yeah, exactly. Does that all make sense to everybody? That was just another thing to consider. I'm going to do an example of like a more complicated version of that, actually, that I remember doing in parallel processing. Yep, makes sense. Okay, fair enough. So let's just move on to the next one. So I'm going to do this sequentially, but we have a similar problem if we try to do this in parallel, although the approach would be a lot different. So let's just do a little bit of math. So let's say I have matrix A, and matrix A is, let's just say, m by n dimension. So I have m rows, and then n columns. I don't know if I can really fit that. Let's just erase that a little bit. I can't fit this. I need to write smaller. There we go. Okay. So that's just filled with, whatever values, A, B, C, D, dot, 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 E, F, dot, 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 and then we just fill it in, right, until it's filled with whatever values. And then we'll say we have another matrix, B, and this one is going to be n by L, let's just say. So just as a reminder, right, when you multiply matrices, the inner dimensions have to match. So the number of rows in this one has to match the number of columns in this one. Okay, and again, we just have some letters. Hij, let's just say J, K, L, dot, 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 M, N, O. So again on this one, oops, we have N rows and L columns. Okay, and let's just say we want to take A times B. Then if you remember, matrix multiplication, all we do is we take each row and we multiply it by each column and then take the sum, right? So I would take A here and I would multiply it by J, and then I would take B and multiply it by whatever's underneath J, and then add it and then do that. Does everybody seem okay with that, with matrix multiplication? I know I kind of put dots everywhere and just hoped everybody got it, but yeah, good. Hopefully everybody's okay with matrix multiplication. Okay. But if not, totally stop me. I will go off and write it more in detail on the side. So, if I was to just write a program and just take my word that this works, I did work it out earlier. So if I was to just say for int I equals 0, I less than the number of rows. And let's just kind of do this as pseudocode. So let's say we have some place that's going to store the final matrix, and it's just initialized to all zeros. Obviously, you would have to do this with more code, but this is just pseudocode. So, whoa, I can't spell. Initialized to all zeros, or theta if you're more inclined. Yeah. I plus plus. Int J equals 0. J less than columns. Oh, I guess I should be a little more specific on this. A dot rows. B dot columns. J plus plus, and then we do. And I know there is a better way to do matrix multiplication, but I think this is straightforward. So k less than n, so n being the inner dimensions between these. K plus plus. Then final sub I sub j plus equals a sub I sub k times b sub k sub j. So basically what we're doing is we're taking each row by each column. So this is going through each row in A, each column in B, and then on the inside what we're going to do is we're just going to count. So k is just like where we are in the like row or column. So like this would be k equals 0, k equals 0. The one under this would be k equals 1. This would be k equals 1 when we go to put them together. So this one, if we think about what the cache is going to do, only specific variables here. I guess I could have just called this M and L, huh? Let me just pencil that in just so we know. This one is M, and this one is L. We're going to have a similar issue with caching, where we run out of space, and so we might be inclined to get some cache issues. But the real question is, what part of this actually affects that? So out of these, the rows, the columns, and the columns of this one, and the rows of this one, what's going to affect cache misses the most and what is not going to affect cache misses in terms of size. So if I just had a really big row or a really big column, one is going to affect the cache hit rate more than the other. So does anybody have a guess? This one might be a little bit out there, but there is something to consider. Would it be the columns? Yes, the columns of B, right? So that's going to affect it. That's one of the things. Columns B, right? And then there's another one that's going to affect it. And there's kind of a way you can tell from the code. So consider what gets executed more often. So the columns of B get iterated on right here. And then if you notice here, K is also on the inside. So the columns of B are going to affect this, and the excuse me, the inner dimensions, that N here, is also going to affect the runtime. And if we think about why, what we're doing is we're taking this row and multiplying it by every column, right? So this row gets used really frequently, hence why it's right here, right? The row is on the outside of the for loops. It's going to get used pretty much when it needs to be, almost always right in a row, right? We're going to take ABCD, multiply by this, ABCD, multiply by that, ABCD, multiply by that. So we're going to use the first row pretty close together in terms of time compared to the columns, right? Because when I go to the second row, I'm going to have to reuse each column all over again. So if I have a lot of columns, I'm more likely to get cache misses because I'm going to unload these pretty frequently. But this one right here, the ABCD, I'm going to get cache hits pretty frequently because, well, I'm using it over and over again. And so I'm going to get a big hit if I have too many columns in B, or if the inner dimensions of these are pretty big, because I'm going to be more and more likely that I filled up the cache and then lose this stuff that I need to use again. Does that make sense as a more complicated example of when you need to consider when you're going to get cache hits, and then, you know, we have to find some sort of solution if we can around this? Yeah, yes. Okay, sweet. So that's about all I had for today. He did just want me to cover 5.1. I just figured I'd go into excruciating detail on programs. Yeah, so did anybody have any questions at all regarding any of this material or anything previous? Oh yeah, sorry.
So how would you go about fixing cache problems for a program like this?
Good question. So it kind of depends on your program. So either the bad explanation I can give is just buy a better processor with a bigger cache. But obviously that's not realistic all the time, right? Sometimes you just can't fix it. Sometimes you can't get around it just because you have that amount of data. In this case, I don't think the other algorithm for multiplying matrices is any better with cache hits. But you might have a problem where you can come up with like an unconventional solution where you're going to reuse the same memory more frequently. So I think the parallel processing version of this is way different. We kind of like shift the columns and do a bunch of crazy stuff. You might want to rethink the way you're solving the problem so that you're reusing the same memory as often as possible. The main problem there is once it gets too big, sometimes there's not really a way around it. Sometimes you just have so much data that you can't fit it in the cache no matter what, and your only solution is just to buy a better processor. Did that make sense?
Yeah, that makes a lot of sense.
It's always practical to consider cache when programming. Generally, yeah. I don't know how much a compiler would optimize cache hits for you. Compilers in general will try to optimize temporal and spatial locality without you even having to think about it. Like if I was to do, bad programming practice. So we need to solve it with cache. Well, you're not solving it with cache. The cache is already implemented for you. It's part of the hardware. You need to program around it. I guess it's the point I'm trying to make. Sometimes you'll get limited by the fact that the cache might get cache equals more cache. Maybe, if you're lucky. The cache is something you have to program around rather than something that's beneficial. I mean, obviously it is beneficial. It speeds up, versus just doing memory accesses. But you have to be aware of when you're going to have caching problems because you can't really control it directly. Yeah, I think the reason I opened this was... Yeah, it's fine, whatever. So if I write something like this in C++, I can't use I. X equals 0, X less than I. Let's just pretend I've initialized these somewhere. No. Sorry, other way around. J. X plus plus. Y equals 0, Y less than I. Y plus plus X sub. Oh, this was really bad naming on my part. Let's just go back up here and name this array. R X sub Y equals 0. Should say I have code that initializes that to 0. The compiler will fix this for you, but the compiler won't fix caching issues generally. I'll give you a second to look at that while I look at the other questions, but this has a problem, and hopefully you notice it. Most often occur when there's a lot of data being handled. Yes. So it occurs when you have too much data to fit in the cache itself. So that's when you're going to start getting cache misses, at least if you've already used that variable. Again, if you're going to only use a variable one time, then you're not really going to get any benefits out of the cache anyways, because it's just going to have to keep loading each new variable that you bring in. But yes, if we get a lot of data, it's more likely to get kicked out or overwritten. And then in that case, you need to also consider how frequently you're using these variables. You want to use the same variable as many times in close proximity as possible, because then it's more likely to still be in the cache and not be overwritten. And I guess, does it make sense why this is messed up? The compiler will fix this for you, but it won't fix caching problems. I guess was the point I was trying to make. So this one accesses columns first, as you didn't notice. It accesses columns first, then rows, and that's not how things are stored in memory, so you're going to have some spatial locality problems. But the processor, or not the processor, the compiler will actually flip these two when you write this, because it recognizes that that's not good, and it will fix it for you. We'll talk more about that tomorrow in discussion, because I have a problem for that, I think. When will the homework for this weekend be assigned? I guess whenever Dr. Fonseca is free? I'm not too sure. Probably tomorrow, maybe tonight. I think he said something on Discord. Do you know anything about the homework? No, I don't. I really only know about the book problems. It will be, sorry, I don't know. He writes all that. I don't know anything about it. Any other questions on caching or just anything in general? If not, I guess we'll probably just end a little bit early. The address problem that takes 10 minutes to solve, that will be on the test, would be nice to solve on Friday. If you come up with a specific number for that, I'll look it up tomorrow. Would we learn about the compiler handles cache in compilers? No. Oh, does he take attendance today? If so, you might just want to post in the chat and I'll copy it. Compilers? No, because I don't think the compiler does any sort of handling of the cache. It just handles temporal and spatial locality problems. Because I don't think it can really address the cache without doing... I mean, if it does it in temporal, it kind of takes care of it a little bit. The compilers class more so covers... I mean, the actual, like, compilation stuff more than optimizations. Usually more like the basics, like how do I convert this program to actual machine code. Cool. Any other questions? Oh yeah, I think somebody else asked a question. I just didn't see it. Do you know how modern CPU get a cache hit rate around and above 90%? I'm not entirely sure of like all the stuff that goes into that. I know there are methods for updating the cache. So the most straightforward one, which was the one I was assuming we were using, was least recently used. So the variable that hasn't been used for the longest amount of time gets thrown out of the cache first. There might be some other stuff they do in there. I know associative caching apparently helps with hit rate, but I only really know a little bit as to why. So I'm not sure of all the details, unfortunately. Sorry if I couldn't answer that question super well. Any other questions anybody had? Okay, well, if there aren't any questions, I'll probably just stick around for maybe 5 minutes and just see if anybody has questions, and if not, I guess you guys are free to go, and I'll see you tomorrow in discussion.
Thank you.
No problem. Take care.